Hello everyone, welcome to my YouTube channel. So today I am going to discuss the complex analysis solution of CSI and NET December 2023. So I will not write down the full question because it takes much time. So that's why I will mention the question ID and I will do the solution. Okay, so please check the question paper and match the question ID and see the problem. Okay, let's start. So first I'm going to solve the question ID number 704034. So this is a very simple problem. The question says that if being a meromorphic function on an open set containing the unit circle C and its interior, f has no zeros and no poles on C, let np and n0 be the number of poles and number of zeros of f inside C respectively, then which one of the following is true? So we need to find out the value of 1 by 2 pi I integral on C zf prime by zf dz. So let zz equal to z times f. Then the integral becomes 1 by 2 pi I integral on C g prime by g dz. So by argument principle, this value is equal to number of zeros of G in C minus number of poles of G in C. Okay. Now G equal to Z times F. That means number of zeros of G equal to number of zeros of F plus 1 and number of poles will be same. So hence the answer is number of zeros of F plus 1 minus number of poles. So option 1 is correct. This is easy one. Go to the next one. So the next problem, okay, so this problem is very interesting. So question ID 704033. Okay, we have the upper half plane, that is z belongs to C such that imaginary z is greater than 0, and we denote a function f from C to C defined by fz equal to e power iz. Then we need to find the image of h and conclude all the options. So all the options are related to image of h, right? So let's first find what is the image of h under this map. So f of x plus iy is given by e power I times x plus iy, which is same as e power minus y plus ix, which is same as e power minus y cos x plus I sin x. So let image of x plus iy equal to u plus iv. Then u plus iv equal to e power minus y cos x plus e power minus y sin x I times. So this will imply u equal to e power minus y cos x, v equal to e power minus y sin x, right? Then we can see u square plus v square equal to e power minus 2y, right? So the element in the image are on the circle of radius e power minus y. So actually what is happening here, if I fix any line parallel to x-axis, that means if I fix y Okay, that means y is fixed but x can be anything, so it is parallel to x-axis. Then it will go to on a circle of radius e power minus y. So something like, if I have a straight line like this in C, then under this map it will goes to this circle. Okay, now I need to find out the image of H. H means upper half plane. So upper half plane means for H, y is greater than 0. Okay, y is greater than 0. That means e power minus y, it will be from 0 to 0 less than e power minus y less than 1 for y greater than 0. Right? So that means image of H will be punctured disk. Is it clear or not? Why this is punctured disk? Because if you, let's draw a picture. So this is C, right? And this is the map e power iz. Okay, so upper half plane means this portion. Now in this portion, if you fix any line, say this is the line, okay, that means y is fixed, and if you see the image of this line under this map, this will gives you a circle with radius e power minus y. If this is y, then this will gives you radius e power minus y. Now upper half plane can be thought as a union of this strip, union of this line, right? For every y you can take this line and then take the union, and for each y you will get a circle like this. Each y you are getting a circle like this. That means you are getting all the circles centered at 0. But 0 is not included here. Why? Because it is e power minus z. The map is e power minus z. That doesn't attend 0. As well as the mod z equal to 1, the boundary of the disk, that is also not attend. Because we have 0 less than e power minus y less than y. So if we include upper half plane union this x-axis, then it will attend this mod z equal to 1 circle. But in upper half plane we are taking imaginary z greater than 0. So that's why the image is clearly this disk, unit disk minus 0, punctured disk. Now it is easy to check all the options. So clearly f of h is not c minus 0, so that is false. F of h intersection h is countable, that is also false, because f of h intersection h means it is this portion, which is clearly uncountable. Right? Okay. F of h is bounded, this is correct. And f of h is a convex set of C. This is not correct because this is punctured disk. So that's why third one is correct. Okay, go to the next one. So the next problem says that f from C to C is a real differentiable function. So real differentiable function means any map from C to C, if you write x plus iy equal to u plus iv, you can think this map as R2 to R2, sending x comma y goes to u comma v. So it is just given that f is real differentiable, nothing else. It is not given that f is analytic or anything like that. Okay. And then they are asking 4 options, which one is the correct answer. Okay. So first observe that if u u equal to c1 and v equal to c2, they are orthogonal. That means suppose this is u equal to c1 and say this is say u equal to c1 some curve, this is say v equal to c2 some curve. So these are orthogonal means if you draw at this point, that means if you draw the tangent vector here and if you draw the tangent vector, sorry, if you draw the tangent vector here, okay, orthogonal means the angle between these two tangent vector is 90, right? So what does it imply? So how to draw the vector here? What the vector looks like? The vector is gradient of u at that point, at point x, which is given by ux comma uy, and similarly gradient of v at point x, I mean x, it should be z because otherwise it will be confusion of notation. I am assuming this coordinate is z, which is x comma y, okay, then it will be vx dot vx comma vy, and this is orthogonal means their inner product is 0. That means you will have ux comma uy, this vector dot vx comma vy, this vector is 0, which is same as ux dot vx plus uy dot vy equal to 0. But it is just given that f is a real differentiable function, nothing else. So you can easily take such function that doesn't satisfy this condition. How do you get that? Say just take this. Let say f equal to r2 to r2. F of x comma y is given by say x comma y square. So what is ux? Ux equal to 1. Vx equal to not x comma y, it is not y square, or yeah, you can do y square also. Say this is y square, so vx is 0, uy is 0, but that satisfies the condition. Let's take some different example. So you can take anything because this is very strong condition. This is not necessarily satisfied, right? Take something like x plus y. What will you get? Ux vx will be 1, uy will be 0, vy will be 1. Then you can see that ux dot vx plus uy dot vy is 1 always, which is not equal to 0 at any point. So whenever they are intersect, it is not necessarily true that that will be orthogonal. Okay, so that's why option 1 is definitely false. Similarly, option 2 is also false because this example also satisfies, because this is R2. If you consider it from R2 to R2, this is real differentiable, right? X comma x plus y. This is real differentiable. You can just find its Jacobian matrix, that is 2 by 2 matrix, simple 1 1 0 1. That is easy, but it is not necessarily satisfying this condition. Okay, okay. Now come to the third part, option. Third option says that if f is entire, then this will satisfy. So if f is entire, that means f of x plus iy equal to u plus iv. That means f satisfies Cauchy-Riemann equation, right? Cauchy-Riemann equation. So f satisfies Cauchy-Riemann equation. Now that means ux equal to vy, uy equal to minus vx. Our given condition is ux plus vx, ux times vx plus uy times vy. So ux equal to vy, that means vy times vx plus uy equal to minus vx, so vx minus vx dot vy, which is 0. That means if f is entire, then f definitely satisfies this condition. So third option is correct. Now fourth one is saying that if this condition is satisfied, then f is an entire function. Clearly not. You can in particular take say fz equal to z bar. is not entire, right? But here u is x and v is minus y. So ux is 1, uy is 0, vx is 0, vy is minus 1. So you can see that ux times vx plus uy times vy, that is 0. Okay, but f is not entire. Hence, third one is correct. Okay, go to the next one, next problem. This is very easy problem, just application of Rouche's theorem. Same type of problem came in many times in this exam. So the function, you need to just take the functions very well so that you can get the answer. 6z plus 1. So take fz equal to minus 50 z power 30, gz equal to z power 100 plus 40 z power 10 plus 6z plus 1. So mod zz less equal to 1 plus 40 plus 6 plus 1, which is 48, and mod fz equal to 50 z power 30. So on mod z equal to 1, you will get this is 50, which is greater than 0. So mod fz greater than mod zz on C. So number of zeros, that means f plus g has same, and f and g both are analytic, so there is no pole. So f plus g has same zeros as f in C. Okay. So together with the multiplicity. So f plus g is our required function, the polynomial z to the power 100 minus 50 z power 3, so on, and f is minus 50 z power 30. So number of zeros of f is 30 together with multiplicity. So f plus g has same number of zeros. So 30 is the correct answer. Okay, go to the next one. This is very simple one, so that's why I don't want to waste much time here. Okay, so go to the next one. Takes time to find out the question. Okay, so I think in MCQ sections there are 4 problems are there. I think I have already solved the 4. 1, 2, 1, 2. This is the third one, and this is the fourth one. So IDs are 704033, 34, 35, and 36. Okay. Okay. Now this is ID number is 704082. So for every n greater or equal to 1, consider the entire function. Consider the entire function Pnz equal to summation k equal to 0 to n z power k by k factorial. That means Pnz, for each fixed n, Pnz is a polynomial of degree n. So we can easily see, everybody knows that Pnz is a power series. I mean, I can think it as a partial sum of the power series summation k equal to 0 to infinity z power k by k factorial, which is basically same as e power z. And since radius of convergence of the power series is infinite, we can take any compact set, it will uniformly convergent. So hence, on any compact set, compact subset of C, Pnz uniformly converges to e power z. Uniformly convergent to e power z. Okay. So that's why the first option is correct. Now what about the other three options? So there is some important observation. Okay, so let's see. So consider fz equal to pnz by e power z. Okay, so fix an n and fix a natural number n and define fz equal to this and set zz equal to 1. Okay, so if 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 we consider, say, snz equal to pnz by e power z, then snz converges to 1 uniformly on any compact set, right? Because pnz converges to e power z, so pnz by e power z converges to e power z by e power z, which is 1. So snz converges to 1 uniformly on any compact set, right? Okay, so now my claim is that, an important claim, so claim for any r greater than 0, there exists a natural number k such that pnz has no 0 in mod z less than r for all n greater or equal to k. This is my claim. So for any r greater than 0, there exists a natural number k such that pnz, the pnz is given by this, we started with this, that partial sum of the power series z power n by n factorial, that power series. So pnz has no zeros in mod z less than r. Okay, so why this is true? So observe, snz converges to e power z uniformly on any compact set, right? So in particular we can say pnz by e power z converges to 1 uniformly on any compact set. That means we can take the compact set to be closure of the closed disk of radius r in particular. Okay, closed disk of radius r. Okay, so right. So from the definition of the uniform convergence, from definition of uniform convergence, what we can say? We can say for any epsilon greater than 0, there exists natural number k such that mod pnz by e power z minus 1 less than epsilon for all n greater or equal to k and for all z belongs to this, right? This is the definition of uniform convergence. Now let epsilon equal to 1. Find k naught satisfying this condition, satisfying the condition. So pnz by e power z minus 1 less than 1 for all n greater or equal to k naught, and for all z belongs to this. Now take fz to be pnz by e power z for any n. So fix an n which is greater or equal to k naught and consider fz to be this. Then fz minus 1 less than 1 for all z this, and if we have already assumed gz to be 1, that means mod fz minus gz less than mod gz on mod z equal to r, because it satisfies for all z belongs to the closed unit disk, so in particular on that boundary also. Then by Rouche's theorem, again by Rouche's theorem, number of zeros, all here all are analytic, so there is no chance of any poles or anything like that. So by Rouche's theorem we can say number of zeros of f same as number of zeros of g, but g is identically 1 constant function, that means it has no zeros, that means f has no zeros on this mod z less than r, right? F has no zero, and so we can take f to be pnz by e power z where n is greater or equal to that k naught, hence our claim follows. So for any r greater than 0 we can choose a natural number k. Okay, here the natural number is k naught such that pnz has no zeros in mod z less than r for all n greater or equal to k. Hence our claim follows. Now in the question it is given that r equal to 2023. That means we can always find some k naught depending on this 2023 such that after that if you choose any n, pnz has no zeros on mod z less, no zeros on the disk mod z less than 2023. So 2 is wrong. Now come to option 3 and 4. It is saying that there exists, so option 3 and 4 both are true, that follows from the this claim also. Why? So first of all think that for each n pnz is a polynomial. For each n pnz is a polynomial, that means it must have a root in C. In particular, pnz is a polynomial of degree n. That means if I consider the multiplicity, that means pnz has n roots in C. Okay. So now what you can do? Here it is 0. Say this is radius 1. Okay. This is mod z equal to 1, this disk. So by this claim, there exists a k depending on 1 such that pnz has no zeros in mod z less than r. That means after that k, all the zeros of pn are outside of this disk. Now take r to be 2. So for r equal to 1, you will find k1 such that for all n greater or equal to k1, zeros of pn are outside of this disk. Now take r equal to 2. Then you will find k2 such that for all n greater or equal to k2, all the zeros are outside of this. Again you can do for r equal to 3 and so on. That means you will have a sequence of 0 pn zn which is 0, but mod zn tends to infinity. Because at each stage when I increase the radius r, we will always find a natural number k depending on that radius such that for all n greater or equal to that radius, all the roots are outside of this disk. So all the roots are outside of this disk. That means if I increase this radius, all the roots are getting outside of this disk. Okay, so that means all the roots are getting outside of this disk. Means if a root is outside of disk mod z equal to r, that means that root, for that root mod zn is strictly greater than r. So hence for any r, so in particular for any r, you can take r to be natural number. You will always find n such and always find a k such that for every n greater or equal to this, mod zn strictly greater than r. That means mod zn tends to infinity. In particular, if you choose r to be n, then depending on some n, mod zm strictly greater than n. So if you consider it as a sequence, it will goes to infinity. So Pn Zn is 0. This is a sequence of 0, but mod Zn tends to infinity. And fourth one is also correct because that is considering the zeros with minimum modulus. Okay, so for each n there are n many zeros. They are considering an to be that zero which is minimum modulus. But see, whenever we are considering any r, we can choose a k such that for any n greater or equal to k, all the zeros are outside. That means the minimum zeros also has modulus greater than r. It is not about just a single zero, this zn. For Pn, it is not about the single zero, it is about all the zeros, right? So hence, in particular, the zeros with minimum modulus also greater than r. Hence, option 4 also follows, right? So I hope this is clear. It takes much time. So 1, 3 and 4, these are the 3 options. Okay, these are the correct options. Go to the next one. Let's search the next question. Okay, the question number 79. Sorry, not question number 78, ID number 704079. So it says that x be an uncountable subset of C, f from C to C are entire function such that for each z, if there exists a natural number n such that f and z equal to 0. So consider a set an equal to collection of all z such that f and x, sorry, z equal to 0, right? Okay, so since f is entire, all of its derivative is entire, right? So fkz is entire for all k, right? Also we know that zeros of entire function isolated unless f is identically 0. So I am assuming that f is not identically 0. Okay, I am assuming that f k is not identically 0 for any k. That means zeros of any entire function isolated is isolated set. Zeros are isolated if unless it is identically non-zero. That follows from the identity principle. Okay, right. Now, and cardinality of isolated set in C is at most countable. Okay, this is a basic topological fact. I don't want to discuss it here because it takes a huge time. Maybe I will make a separate video for particularly this, but this is a standard result. So that means it is at most countable. So either it is finite or it is countably infinite. That means cardinality of an for any n is at most countable, at most countable. countable for every n. Is countable. So countable union of countable set is countable. That means union of n is countable, right? But x is uncountable. That will imply x not equal to union of n. So hence there exists a x belongs to x such that fn x non-zero for all n, which is a contradiction to our given condition, because our condition says that if we choose any element x, there exists a natural number such that fn x is 0, right? So that's a contradiction. Hence there exists k belongs to n such that ak is uncountable, right? That means zeros of fk cannot be isolated. In particular, then fk is identically 0. So if fk is identically 0, that means fn is 0 for all n greater or equal to k, right? So hence f is a polynomial, and this is also a basic result that if f is an entire function such that there exists some positive number k such that fk is 0 for all k, that means f is a polynomial of degree at most k minus 1. Polynomial of degree at most k minus 1. Okay. So f is a polynomial of degree at most k minus 1. So hence f equal to 0, that is false. F is a constant function, that is also false, because it is not necessarily true options. So option 4 is correct. And now if we have a polynomial, we know that polynomial satisfies this condition that if mod z tends to infinity, mod pz tends to infinity. So if k is any compact subset of C, that means k is closed, and f is entire means f is continuous. So f inverse k is already closed. There is nothing to check here. So only thing we need to check to whether it is f inverse k is compact or not, that is f inverse k is bounded or not. But if f inverse k is unbounded, that means there exists some sequence such that mod zn tends to infinity, right? If f inverse k is unbounded, but that will imply that mod pzn tends to infinity, which implies that k is unbounded, which is a contradiction. So hence for every compact subset k, f inverse k is compact. That's why only option 4 is correct. Okay. Now go to the next one. So what is the next one? Next problem. It says that omega 1 is z belongs to C such that mod z less than 1, and omega 2 is capital C, right? So which of the following statements are true? Okay, so mod z belongs to C such that mod z less than 1 and omega 2 equal to C. So it is easy to check. That it is basic fact that we know that bounded entire function is constant. Bounded entire function is constant, right? Bounded entire function is constant. Okay, so if we have a holomorphic map, then bounded entire function is constant. So clearly option 2 and option 4 are false. Why? Because in both cases the map is from C to the unit disk. That means image is already bounded. Hence bounded entire function is constant means it is constant. Sorry, bounded entire function is constant, that means it is constant. So option 2 is also wrong, it cannot be surjective, as well as option 4 is wrong, it cannot be injective, because the map is constant. So only left option is option 1 and option 3. So option C says that there exists a holomorphic injective map from open unit disk to C. So in particular you can take fz equal to z, the identity map. This is an injective map from omega 1 to omega 2. Now the interesting part is option 1, that there exists a holomorphic surjective map from f omega 1 to omega 2, where omega 2 is the whole complex plane and omega 1 is open unit disk. Okay, so whenever you have any open unit disk, always try to connect with upper half plane, because we know that open unit disk and upper half plane are biholomorphic. Open unit disk and upper half plane are biholomorphic. So sometimes if you have any problem to give a map from open unit disk, you can in particular give a map from upper half plane if it is easier for you, and then compose it with this biholomorphism. That will give you the map from disk to that particular target set. Okay, so here also we are doing the same thing, because from open unit disk to C, the giving a surjective map is quite difficult. So that's why we will try to give it from upper half plane. So say we have this upper half plane, and we are trying to give it a map from map to C, right? So can you imagine that? Can we give a map from this to this? Yes, we can give. How we can give? So suppose we give the square map. What will you get? So here it is I is here. So I is here means I square is -1. That means -1 is also here. So if you pick up any element here, so that must have a root, because z square equal to a, this must have a solution, and you will have a solution such that mod z, imaginary z is greater than 0. Okay, so that's why you can take the z square map. But here is a problem. The problem is that this real axis, you can't get this real axis if you take the z square map. Why? In particular, if you take 0, so pre-image of 0 under this z square map is 0 itself, but 0 is not in the upper half plane, because upper half plane means imaginary z is strictly greater than 0, right? So what will you do? Just translate it. So you have this, just translate it by some, say by just 1, translate by 1, okay, then you will get this. Now you apply z square map, you will get the whole C. Okay, you will get the whole C. That means how do I get the surjective map? So I have this open unit disk, I apply the biholomorphism and get the upper half plane, translate below by 1, you can do half or 2, anything, so you will get this, then apply z square map, you will get the whole C. This will gives you the surjective map, right? So always try to connect it with upper half plane, that will be easier for you. Okay, and I think only one question is left. Let me check. Yes, and that is just very simple problem, that it is given that ik is mod z equal to 1 e power z by z power k. So we know that by Cauchy integral formula for derivatives, we'll have that if k minus 1 0 is k minus 1 factorial by 2 pi I, k minus 1 factorial by 2 pi I integral mod z equal to 1 e power z by z power k dz. So then you get the formula for, and here f is where fz equal to e power z. So derivative of f, all the derivatives of f is same, right? So hence you will get the answer, right? So that means if k minus 1 0 is 1 always, so value of ik is 2 pi I by k minus 1 factorial. Now what are the given options? From the given options you can see that option 2 is only correct, because ik is always non-zero if k greater or equal to 1. Okay, ik is always non-zero. If k equal to 0, then the integral is just e power z dz mod z equal to 1, and e power z is holomorphic, so by Rouche theorem that will be 0. But for k greater or equal to 1, this is non-zero. So only option 2 is correct. Right, option 2 is correct. So these are the all problems and these are the all solutions. There are 8 problems. Okay, I hope this is clear. So, and this problem ID is 704081. 704081. Thank you.